Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver, and today we're going to talk about adding vectors. I think it's important before we start talking about adding vectors, we know what a vector is, right? So it's important to try to understand what a vector is for physics and just in general, but more importantly for physics. So when we think of vectors, we want to think of vectors as a way to draw a number, right? It's kind of weird, it's abstract, but it's how we draw a number. And why is it important to know how to draw a number? Kind of a weird thing. Well, because we're going to be dealing with physical values in here, and we're going to have to draw a lot of pictures, and we don't want to be drawing numbers everywhere. It makes the picture real messy. And if we can just show vectors, right, and their sizes become their values, and the way that they're pointing becomes the direction that they're facing, we can look at a picture and it can tell us a lot more, right? So those vectors have to be correct in terms of value and size when we're making a picture based off the scale that we have, right? So if I have two vectors that are the same, so again, I'm on a machine, so that are roughly the same size, I'm saying that this might not be, anyway, it doesn't have to be perfect, but the same size, right? If I put them together, the new vector better be double the size, okay? So, and that's just how numbers work, right? If I have 5 and 5, the number that they produce is 10, right? Just here we also have a direction that the way that they're pointing, but vectors work like numbers. So the way that we can add, subtract, multiply numbers, we can do the same thing with vectors, and we're going to learn all that, not in this video, but as we work through physics, we'll learn how to do all those things. If you don't know how to do them already, you may already know, and this may just be a good refresher. So again, what is a vector? A vector is the way we draw a picture of a number or a physical value here in physics. A vector is going to have a magnitude, which is going to be their value, their number value, and then a direction. We're going to state the way that they're pointing, okay? All right, so how do we add vectors? Well, there's only one real true method to add them, and we kind of separate these. And by the way, this video is paired with a second video for subtracting vectors. So after you're done watching this one, make sure you also watch that second video about subtracting vectors because it goes along with this video. We refer to this video a lot, and so you want to make sure you know what's going on, and also try to watch it right after because the closer you watch those together, the better it'll be. But here, right, we're going to talk about directly just addition of vectors. So how do we do that? The method is what you'll hear from most of us called tip-to-tail. Even though we may say it a little bit different, that's what we're doing. We're putting tips of or tails of vector to tips of vectors in a sense, but that's less important. So how does this thing work? So when we add vectors to do the tip-to-tail method, the first thing you've got to do is locate your vectors. Don't just look at your paper and say, oh, hey, look, or the question on your test or whatever, and say, look, there's my vectors, and just look at them. Yes, we know you can see them. What you need to be doing there is you need to be locating, not just looking at them, but saying, hey, which is my first vector, second vector, third vector, how are they given so I can line them up appropriately, right? Because you have to line these things up in the right order. It's important. It helps you give just kind of a logical, sound way to solve these things. So make sure that you not only look at the vectors, but you locate the order, right? If they weren't told, like V1, V2, V3, the first vector is the first one given. The second vector is the second one given, right? Just like numbers. If I were to give you 5 plus 5, 5 is the first number given, right? So just like I'd give you two vectors, A is the first vector given. Remember, these are just like numbers. They work the same way. So everything you do with numbers, try to think, hey, vectors work the same way. I'm just kind of drawing a picture of how I think of numbers. Instead of adding 5 plus 5, I can add two vectors that would be equal to the size of what I would consider 5 in terms of a scale, and hopefully they equal 10. So, after you've located your vectors in their order, you want to draw the first vector. You locate the first vector and you want to draw it. Sorry, I kind of said that word. So you want to look, after you've located the order of vectors, draw the first vector, and then you want to take the tail of the second vector and place it at the tip of the first vector, okay? And then every vector after consecutively. So then after you place the tail of the second vector on the tip of the first vector, if you have a third vector, you'll place the tail of the third vector on the tip of the second vector. You have a fourth vector, you place the fourth of the vector, fourth vector, tail of the fourth vector on the tip of the third vector. That is a tongue twister. but I'm sure you get the picture. All right, and then after you've lined them all up, how many are there? Sometimes there's 2, sometimes there's 3, sometimes there's 8, however many. After you've lined them up, okay, you want to draw the net vector, which is going to be their sum, right? Sometimes they're subtracting or adding, but their net vector from the tail of the first vector. So if you have 80 vectors all lined up tip to tail, you're going to draw the net vector from the tail of vector 1 to the tip of vector 80. That's out of all those vectors that you have lined up. Or if you have 3 vectors, right, you're going to draw from the net vector is going to be drawn from the tail of the first vector to the tip of the third vector. Okay, you kind of ignore 2 because you're just drawing from the tip of from the tail of the first vector that was drawn to the tip of the last vector drawn, wherever it is, even if it's in the X or Y. Okay, we're going to practice this a lot. Here's just a little orientation. I'm sure you guys are well aware, but right, we know we want to make sure when you look at a vector, you know what tip to tail is. So the tip of the arrow is obviously the tip of the vector. The tail of the arrow is obviously the tail of the vector. So let's kind of get going and apply this idea, right? Okay, so here's one addition, how to add 1D vectors. We're going to look at also 2-dimensional, how to add 2D vectors as well, but this one's a little bit more straightforward. So if we have 2 vectors like I was showing you, I've kind of been referring to this example quite a bit, but if we have 2 vectors there, and I want to make sure you can kind of see some separation here, there we go, and they could be called A or B, right, or they could be called, given some number. You don't really want to write the number up there, but I'm just trying to show you. You want to draw your first 2 vectors, right, or if they're given like this, you want to locate your first vector, locate your second vector, then you draw your first vector, which is A, then you take the tail of your second vector, which is B, and you place it at the tip of the first vector, like we see right there, right? And then we draw the net vector. You look for more. Hey, there's no more vectors, there's just 2 here, right? If there were, we do another one, right? But there's not. And then, so we go to step 3, which is draw the net vector from the tail of the first, or A here, to the tip of the last, which is B. And so if these are numbers and these are 5, then these are both 5, we should get 10, right? That's the way these would add together if they were numbers. If you had to give a numerical value, that's how you do it. But if we ask for a picture or a graphical way to do this, you would show us this picture only. You don't have to give us a number, but you want to make sure you do have orientation. And if you do give the number, make sure you say the direction. Not just 10, right? This should probably be 5 to the right and 5 to the right, I'll admit. But, right, you want to say 10 to the right, okay? That's how we want to give our answers. With magnitude, what we say, that number value, and direction. If we have to, if we're just asked for the picture, then just show the picture. The green arrow right there is the answer, right? That would just be the picture. All right, let's do it a second way. Now we can see that these vectors are kind of opposite of each other, right? And so when we do the math, yeah, we will be subtracting them, but we can still use the addition method, right? So we can take the first vector that we have, right, and draw it. And then we want to take the tail of the second vector and place it at the tip of the first, which is what we did right there. Now again, yeah, we might want to superimpose that, right? But then we can't see what we need to see. So we draw it above. And then, yeah, now we're on step 3 again, where we're going to look for the net vector, where we draw from the tail, right? This is the first vector, right? So we're going to draw from the tail of the first vector to the tip of the second vector, or last vector, right there. Right, and then so that's going to be our net vector, and if this was a value of 8 and a value of 5, right, this would be 3, and we'd say 3 to the east. Or if we just asked you for the picture, again, then you would want to just give that green, well, you want this whole thing, right? You want those 2 vectors and then showing the net as well. All right, you don't want to give a numerical value, just want to make sure we understand. And again, vectors take on direction, right? So when we do the math, we have to make sure that we give that negative sign, but we also need to understand that vectors, how are they different from scalar values? That negative sign, when we give it to them, we'll talk about it a little bit over here, has to do with direction. Okay, and a way to separate that, because it's like, what are you guys even talking about? Think of temperature, that's the best example. Okay, temperature is not a vector. It's not a vector. It is what we call a scalar value. Okay, why is it scalar? Because when you, for example, drop below 0, we say you're like -5 degrees Celsius, right? That actually means you're under the value of 0 degrees Celsius, right? So that's what we mean when we talk about scalar values. When you have a negative sign, it means less than 0. When you have a positive sign, it means more than 0, right? But with vectors, it's different. With vectors, the sign is the direction, not above or below 0. That's super crucial to understand, okay? It is the sign, just the direction is pointing. So if I have a vector pointing up and I have another vector pointing down, even if I have no direction given, I better give one of them a negative sign and the other one a positive. Okay? It's very, very important we understand that. We'll talk about this over here. Okay, so let's just do a few more again. These are all in the x direction, these are all in the y, these are just one dimension. When you do two dimension, it gets a little bit more complicated. So again, now we're just showing the picture here, right? But if we have two vectors, we want to draw the first one, right? And then we want to, oops, I see that I totally, again, I guess with math, you know, it necessarily doesn't matter, but I have those drawn backwards, so look at that. You get to see me correct this, and I apologize about that. But again, the order is important, and I'm glad you're able to see this because the order is important. That's why I'm changing it, and I'm just not saying, well, just imagine that I drew this way or this way, right? That's not what I want you to do. I want you to actually realize how important that order is, okay? That order is crucial. It's crucial, okay? So we draw our first vector and take the tail of our first vector and put it at the tip of our second, and then draw from the tail of our first to the tip of our last, okay? It's crucial we have it in that order. All right, let's go to our other one here. First we locate our two vectors, step one, and we draw our first vector, right? Then we draw our second vector by placing it at the tip of our first vector, right? Did this one right. And then we want to draw the net vector, right? From the tail of the first to the tip of the second, right? And something I want to show here as well. So let's say that you just looked at these vectors right here. You didn't do any tip to tail. You got to also have a really good conceptual understanding of vectors. It's important. So you should have just been able to look at this and say, well, I have a longer vector down than pointing up. So when I combine these two vectors, there's probably going to be some of this vector left. How long exactly? Yeah, you have to do this. Okay, but you need to be able to check yourself. One thing we do in physics is we look and we try to predict. We say, okay, what's the answer going to kind of be? And then when we get an answer, we can check it and say, hey, does that make sense? And that's a good start to do here, right? Where we can look at this and say, if I end up with an answer where my net vector is pointing up, something's wrong because this vector, these are numbers, right? This is a larger number than this. I better be left over with some value of this, right? And since it's pointing down, there'll be some value pointing down. Look, that's the answer we got, right? Same thing with this. If they're pointing in the same direction, then you better already have a conceptual idea that this thing better be double the length of these, all right? Not having to do, yes, if we need the exact length, you want to do this. But you should already be able to look at those and say, hey, when I put those tip to tail, they're going to combine, right? Just like if you saw 3 and 2, you know that's going to make 5, right? You don't necessarily have to write 3 and 2 down and then 5, okay? All right, so that's all one-dimensional. What the heck's going on with 2 dimensions? All right, well, it's not too difficult, but before we get into that, we kind of want to talk about something real quick, all right? And it's something called components. So, like we were saying, vectors are numbers. You want to think of vectors as numbers. And if vectors are numbers, right, every number, like this 10, this number, I don't want to get into details here, right, but when we look at numbers, right, a lot of numbers could have numbers, 2 other numbers that when added together can make their whole, right? So this is the whole of these 2 values, right? So vectors at an angle, they kind of have pieces that make their whole, right? When they're all drawn in one direction, that's their whole, A, right? It's only going in the x direction, so its whole value is in the x. But when it's kind of shared in the x and y, we have x and y pieces to this vector. There's not just an x value or a y value, right? So we want to think of those as the pieces of the whole, where that 10 would like be that vector and the 5 and 5 would be the pieces of it. But here, the 5 and 5 would be an x and y value, right? Not one in the same direction, which is what we're going to talk about here. But it's really important, right? Everything can have pieces. Like 10, there's a lot of ways I can get to 10. 9 plus 1, right? 8 plus 2, 5 plus 5. The point is that these numbers right here, 8 plus 2 equals 10. The 8 plus 2 would be considered the components. 9 plus 1 equals 10. The 9 plus 1 would be the components, okay? So that's what we want to think about with vectors and vectors at an angle. All right, so how does that work in terms of these vectors? Well, we want to know that when we break them up, there's two ways to always break these vectors up based off the angle that we're given. All right, and also when we're drawing the components of these vectors, we want to make sure that we're enclosing that angle that was given to us, right? One other thing to kind of keep in mind here that hopefully you have a conceptual understanding about is also their direction. So when we enclose that angle, those directions of the arrows are also important, but we want to remember that we can kind of have an idea based off the way the arrow is drawn and the coordinate system that we're given, right? So based off these coordinate systems, I've kind of set up some clues for you to kind of look at to help you, but keep in mind coordinate systems do set the positive x and positive y. But the way we have things set up here, if I were to draw any component for this vector, whether it's for phi or theta, the x component will be positive and the y component will be positive, okay? It doesn't matter. So if you're getting a negative component, the vector that's pointed this way, where it's sitting between the positive y and positive x, no matter where that positive y and positive x may be on your picture, you're doing something wrong, okay? So you already have an idea of what the sign of those vectors would be. And if you have the arrows drawn in some direction that isn't in the positive x or positive y for either angle, you're doing something wrong. You already know because you have an idea that if you're looking at an angle between positive x and positive y, their components better be positive x and positive y. What if I'm looking at a vector that's in between x and positive x and negative x and positive y, right? Well, then we should know automatically that all the y's are going to be positive, right? Because it's sharing, if it's in between the positive y and negative x, it's sharing some positive y, and then all the x components for this better be negative, all right? We'll get into more detail here, but it's something important to know, because if you aren't getting these, if you're drawing the vectors this way, when the vector that you have drawn is sitting in between a positive y on your scale and negative, or in that quadrant between positive y and negative x. And again, we can twist this in physics, so sometimes positive y and negative x might be this way, but if it's in between those, right, you should know that it's going to have some positive y value no matter which angle you use, right, and some negative x value no matter what angle you use, all right? Same goes for this one, right? Again, but we can see that since it's here, right, since it's kind of split between the negative y and negative x, that the components for this one better be what? Have some negative x and have some negative y, right? The x components better be negative x no matter which angle we use, and the y components better have some negative y, right? And again, that's what we have written here in the green. If you're not catching it, I'm just telling you what's there in the green. And again, this one, since it's sitting in between a positive x and negative x value, right, we know that the components are going to, for the x are going to always be positive, and for the y is going to always be negative, right, no matter which angle you enclose. All right, super crucial. The other thing that's important is that you're able to draw the value, write the value of these components, right? If you're given a vector that's at some angle, you got to be able to write these components in terms of their trigonomic values. That was the reason why we taught you trigonomic functions. Sorry, said that word. So that's why you learn trig. So that's what we're kind of doing here. Now again, I'm going to try to go through everything, but I want to save some time. That's why I have it written here. So you can pause the video, zoom in. Hopefully you're watching this on HD with headphones, because that's what you're going to get. You're going to see the clearest thing, right? The bigger the screen, the better. But you can look at these, and I have every answer written for you for each one, but let's try to get through some of them. So up here, right, for theta, right? So keep in mind, when we have an angle like this, that's phi, and an angle like this, that's theta. Okay, that's just important to know, because that's what I'm going to call these angles here. Okay, so theta and phi. So when we're using theta, right, we know our x component is going to be positive and our y component is going to be positive. And when we write it in terms of our trig function, it's going to be v1, because this vector is v1, right? So the magnitude is going to be v1, and then the trig value, which is kind of explaining the direction of it, it is that part of it, but I don't want to get into that, is going to be cosine theta. And it's cosine theta because why? It's adjacent to that angle that we're writing it in terms of. And again, how do we know that these components are drawn the way that they're drawn? Because this was the angle we chose to use and we wanted to enclose it. That's the first thing that we needed to know. And then we remembered that this better be positive and this better be negative. If you can't remember that, there's another fun way to remember where you think of that you have like a ball right here at the bottom of your main vector, and you want to, in 2 moves, get to the tip of that of your main vector. You want to move from down here to up here in 2 moves, but you can only move left, right, or up or down, right? So if I needed to do that and I was down here, I would move right first, right? And that's the first vector, it's pointed in the correct direction. Then I would move up, and that's pointed in the correct direction, right? So that's another way to kind of get your components. There's a lot of ways to look at it, right? Now, V1y, right? We just did V1x, which is V1 cosine theta. V1y is opposite of theta, so that's V1 sine theta. What about phi? Well, now we see x. That's another thing that's important here. Don't always think x is going to be cosine theta. Right here we see when we use phi, the x is sine theta, okay? So when we write it out, it's V1x is equal to V1 sine phi instead of theta because of the angle we're using, right? And then here, the y is V1y is equal to V1 cosine phi. All right? And again, they're all positive. If they were negative, we would have said negative. We'll see right here in the next one, right? So for theta, V2x is negative V2 cosine theta. We said x better be negative, right? And it is. And keep in mind, when we drew it first, I should have mentioned that first, right? When we want to enclose the angle, and so the way that we enclose theta and get the vectors that we want is we know that it shares a little bit of the negative x. So when we draw the x, it better be pointing at the negative x and sharing some of the positive y. Why do we know that? Because the vector is sitting in between those 2 values, right? So even when you draw your pictures in physics, if that vector is sitting in between whatever 2 directional values, or not, I'm calling them values, but whatever you have in terms of your a coordinate system, whatever 2 coordinates it's sitting in between, that's what these vectors are going to share, okay? Just so keep that in mind. All right, so for theta, right, it's V2x is equal to negative V2 cosine theta, right? And for the y, it's going to be positive, right, V2 sine theta. I know that looks like negative, but it's not. That's for the y. So V2y is V2 sine theta. It's positive, pointing up. Now, if we did phi, x would be V2x is equal to V2 sine phi. Again, it's sine because it's opposite, and it should be negative. Now, there I didn't put the negative. And I should have. So that's V2x is equal to negative. V2x, this one right here, pointed this way, is equal to negative V2 sine phi. And then the y is right here. And for, again, when we're talking about phi, we're enclosing that angle. V2y is equal to V cosine phi. All right, and that one's positive because they're pointing in the positive value. Again, the x is negative because they're negative. Here we can see they're all negative, right? The x's, they're sitting in between this vector, this main vector, V3, is sitting in between negative x and negative y, right? And so we know because it's between negative x and negative y, the components are going to be negative x and negative y, okay? And so if we look at theta, and we want to enclose that angle, and we want to get the components, we know the x is going to be drawn this way, and then the y is going to be drawn this way, right? It's sharing a little bit of those components. Or again, we can play our game where we have the ball right here. We want to move down here in 2 moves, so I'd move right first and then, or sorry, left first and then down, right? If I'm trying to enclose phi. I'm trying to enclose, or if I'm trying to enclose theta. If I'm trying to enclose phi, I would move down first and then to the left. But either way, these end up being the same. And then our values for theta is V3x, right? This is 3, and it's the x direction. That's why we write it like that, is equal to negative V cosine theta. The y is equal to negative V3 sine theta. Here for phi, the x is equal to negative. Again, we got to put those in there. Negative V3 sine phi, and the V3y is equal to negative V3 cosine phi, okay? And then here we know, since it sits between the positive x and positive or negative y, This is going to have positive x components and negative x components, no matter which angle we enclose. So if we look at theta, they'd be positive first, negative y next in terms of drawing the components, or if we look in terms of phi, be negative y first and then positive x next. And then their values for theta, vyx in terms of theta is going to be positive v cosine theta, vy in terms of theta is going to be negative v sine theta, because again it's pointing down, right? Negative v pointing down, and that's negative, right? And that's where that sine's coming from. Just talked about that. And then for the x direction for phi, it's going to be v sine phi, and it's positive again because it's pointing the positive direction. Or for the y, it's going to be negative v4 cosine phi. Okay, so that's how we do all the components. Now we can do this problem. Hopefully, it shouldn't be too bad. So we're given these three vectors, right? If we do just need the picture, right? We don't. What we're doing here is something kind of different. If they're just saying, hey, give us the picture of these three vectors added together, then yes, you can go tip to tail, just like we said here, where we draw our first vector, which is v1, right? And then we take the tail of v2 and put it at v1, right? And then we take the tail of v3 and put it at v2, and then draw the net vector, right, from the tail of the first vector to the tip of the last. So it's going to be drawn from the tail of v1 to the tip of v3, and then that's the net vector here. That's what it would look like, and that would be great if they just asked you for a picture, okay? But it doesn't help you to mathematically look at things here, and it's not going to help you too much in a problem, because usually when we get a vector at an angle, we need to break it up into its components. The reason why is because a lot of these physical values will be given, the vectors will be working independently of themselves. They'll be doing different things. Like for example, when a box goes down a ramp, the weight gets distributed. Some of it goes down the ramp, some of it's just balancing the box on the ramp, right? So some of the weight is trying to pull the box down the ramp, some of the weight is just keeping the box balanced on the ramp so it's not breaking through or flying off. All right, but if we just looked at the weight of the ramp, we wouldn't see that. But when we break it up into the components, we see that. So that's why typically we break things up into components. Here we're breaking things up into components so we can mathematically get an answer, because we're going to need numbers in here too, right? So if we are not just for the picture, we got to make sure that we do this right. So you want to, yes, have multiple pictures here. The first picture you want to have is where you're drawing the components of everything. Now V2 and V3 don't have components necessarily. They're just directly in the X or directly in the Y. Those would be considered their components, but they don't have any X and combined X and Y components, right? Now we see the angle we were given, theta, so we want to enclose that theta, right? And then we know that our main vector sits in between positive y and positive x, so it's going to have positive x and positive y components, right? We can also remember the game where we need to get the ball to the tip of this vector from the bottom of it, where we can only move left and right, enclosing that angle, right? So the first thing we want to do is move right, which would be in the positive x direction, and then up, which is in the positive y direction. Those are components, and those are enclosing the angle. And we want to write their values, right, in terms of that theta. So v1x, right, is actually v1 cosine theta. It's positive because it's in the positive x direction. And then v1y is v1 sine theta, and that stays positive because it's up. Again, sine theta because it's opposite, cosine because it's adjacent, right? Talked about that a lot over there. All right. So the next thing we want to do is, now that we have our pieces, we want to put our pieces together tip to tail, the x's and the y's. All right, and we can see right here with our components that our x and y's can line up together. So once we line all our x's up together, we can then start to line our y's up, starting at the tip of our x's. We don't have to do anything fancy. All right, so like I said, the first thing we do is locate our vectors. So there's my first vector in the x, there's my second vector in the x, there's my first vector in the y, and there's my second vector in the y. Yes, that's v3, but it's my second vector in the y. v2 doesn't have a y, right? All right, so I located them and know their numbers. So I need to draw v1x first, because we like to start with their x first. All right, so I draw v1x right there, right? Then I want to take the tail of v2 and draw it at the tip of v1, which I did right there. And then if there's no more x vectors, then we're done aligning the x. If there were, we'd do another one, but there's not. Okay, and now we can start with the y, beginning at the tip of where our x ended, right? So our first y is v1y. So I grab that and I draw that there, right? Take the tail of v1y and put it at the tip of v2x, right? And then I take the tail of v3 and put it at the tip of v1y, right there. And then I draw, and then I see that I have no more vectors, right? Those are all my vectors in the x and all my vectors in the y. Then I can draw my net vector, right? I'm on step 3, from the tail of my first vector to the tip of my last. V3 is my last, V3 in the y is my last vector. V1x is my first vector that I drew, right, in my order of vectors. So I want to draw the vector from the tip of v1x to the tip of v3, right? We can see it's the same vector, right? Same angles right there, that really small angle, right? I should have drawn these on that line, but I wanted you to be able to see everything, right? But that tiny angle is still on there, so it's the same vector, it's just we're seeing a little bit different. But again, this isn't very nice because it doesn't help us too much. It helps us see the math, but it doesn't help us see our new picture, the total picture we have, right? We have a new right triangle is what we have, and you don't see that there, right? In essence, you don't. I mean, yeah, if you enclose this in, you see it, but, right? We do have that, right? We have a new right triangle when we sum all our x's together, right? So when we take v1x plus v2, right? But in terms of a vector, we draw a tail from v1x to v2, where we have just one total vector, right? And that's what we have here. And then I would draw that net vector from v1y, right? Here's v1y and v3. That net vector would be from the tip of v2 pointing up still, because we know v1y is longer than v3, right? But it'd be very small, right? It'd be right in between the tip of v1, or the tip of v3 and the tail of v1y, right? So it's very small. I didn't draw it in there, but that's it right there. That's v1x added to v3, or essentially we'll be subtracting them, right? So we can see we have our vx total here and our vy total, right, in terms of our vectors, and then we line them up tip to tail. So what are we doing here? We're kind of breaking this vector into its pieces. Now we're getting our new vector, and now we're bringing the pieces back together. We're saying, okay, we have these pieces, right? We just drew these pieces. We knew the x component and the y component of this vector from this picture, right? And so we drew those pieces, right? And then we drew our net vector, a nice pretty picture. And that net vector, again, once they're aligned tip to tail, will go from the tail of the first vector to the tip of the last, right? And that'll be v total. All right, so that's in terms of the picture, trying to do it, letting us see the steps and what we'll typically be doing in a lot of physics problems, all right? But how do we mathematically do that? Very simply, you want to break up something into two columns, an x and y column, right? And then you want to just use those values mathematically to add them up. So v1 cosine theta, whatever number that would be, you would write it there, right? And whatever v2 would be, whatever number we give you, you would write it right there. And you'd add them up, they're both in the same direction, so they'd add, right? And that'd be vx total. And then for the y direction, you'd write the number, you'd get the number for v1 sine theta, right? You'd just put in your calculator, whatever number they give you for v1, and then hit sine, and then put the angle in there, and then hit the parentheses and hit enter, right? You get a number for that, and a number for v3. Now, v3 is negative, pointing in the negative y direction based off the coordinate system we have, right? Everything's positive y, positive x here, right? So vy is pointing, or v3 is pointing opposite of positive y, which means it's negative x, or just a negative value. So when we write it in terms of the number as well, right, we were saying it here, it's all here, right, but when we write the number, we have to include the negative sign to show, right, to show us that you know, we need to subtract it from v1 sine theta, and we do the math properly, and then we get a v1 vy total once we do that math. And then now keep in mind, yes, over here we can just directly add x's and y's, and good, right, normal arithmetic. But to add x's to the y's, you need Pythagorean theorem. So just make sure once you get the x's and the y's, to bring them together, whether you're doing this or anything. If you have two components, right, an x and a y, and you need to add them together, you need to do Pythagorean theorem to add them together. That's how we add x and y's together, okay, where it's just the square root of the vx total squared plus the vy total squared, okay, and you just do that, do the square root of those values, and you'll get the total vector. Again, these are the components in here. This is the x component, this is the y component. It's how we add the x and y components, all right? And then to get our new angle, And that's what these are kind of there for. We can see that our Vx's are adjacent to the angle, and our Vy is the opposite of that angle, right? So we can use tangent theta, right, where Vy is our opposite, right? Tangent theta is equal to opposite over adjacent, right? Where Vy is the opposite, and Vx is the adjacent, opposite over adjacent, right? And then we solve for theta, where we just do the inverse of tangent times Vy over Vx, right? Total, this is Vy total. Keep that in mind, I should have written that. And Vx total, right? The numbers that you got here. So Vy total, you'd write in there that number, and Vx total would go there. All right, and that's the same, these are also total, okay? All right, well, I hope this was helpful. Like I said, this is only one piece. Make sure you go watch the second video for subtracting vectors. It refers to this a lot, and you will need it. All right, and then watch both together and watch them multiple times, all right? I hope you're having fun in physics. It is a really, really cool thing, but we really need to understand these fundamental pieces in order to do it, all right? I'm super proud of you, and I'll see you on the next video.